You are 380,000 kilometers from home. The moon fills your entire window. In 2026, humans are flying around it for the first time in over 50 years. They won't land. They won't even slow down. But that's only level 1. Your ship is called Orion. 4 people inside. The mission is simple. Fly to the moon, go around it, come back. No landing, no stopping. 10 days, start to finish. You launch from Florida on the most powerful rocket ever built, the SLS. It burns through 3.3 million liters of fuel in 8 minutes. By the time the engines stop, you are already moving at 28,000 kilometers per hour. For 3 days, the moon grows larger. You watch it through a small window, grey, silent, covered in craters that haven't changed in 1 billion years. No wind to erase them, no rain, no weather at all. On day 4, you pass behind the far side. Earth disappears, no signal, no contact. For 30 minutes, you are more alone than any human has been since 1972. The last time anyone saw this view, it was the crew of Apollo 17. You are closer to the moon than any human in over 50 years. 9,000 kilometers above the surface. You can't see individual rocks. But from here, the craters look close enough to fall into. The ground is grey, dry, completely still. And you are flying past it at thousands of kilometers per hour. You want to stop. You want to go down there. But that's not what this mission is. This mission is proof. Proof that humans can travel this far again. That the machines work. That the math is right. The moon shrinks behind you. Earth grows. 10 days after launch, you land in the Pacific Ocean. You traveled over 2 million kilometers, and you never touched the surface. Not yet. The next mission doesn't fly past. It goes down. You are inside a lander, not a small one. This thing is 50 meters tall, a 15-story building standing on rocket engines. It separates from Orion in lunar orbit and begins to fall toward the surface. The engines fire. Dust flies away in perfect arcs. There is no air to slow it down, no wind to make it swirl. It hits the ground as fast as it left it. The lander touches down. Silence. No wind, no engine noise, nothing. You open the hatch and step outside. Your boot sinks about 2 centimeters into fine grey powder. This is regolith. It covers everything on the moon, and it is one of the most dangerous things here. Regolith is not like sand. It has never been smoothed by water or wind. Every grain is sharp like broken glass. It cuts into fabric. It scratches visors. It sticks to everything because it carries a static charge from the sun. On the Apollo missions, it got inside the suits. It got inside the lungs of astronauts. Some of them were sick for days after they came home. You walk slowly. Gravity here is 1/6 of Earth. You weigh about 40 kilograms in your suit. Every step feels light. You feel strong, almost too strong. But there is very little grip between your boots and the ground. You don't walk, you skip. And because your body and suit still have all their mass, stopping is hard. You slide like you're on ice, but the ground is bone dry. The landing site is near the South Pole. NASA chose this area because there is ice here. Frozen water hidden in craters that haven't seen sunlight in 2 billion years. Water means oxygen. Oxygen means you can breathe. But first, you have to dig it out of ground that cuts through almost everything it touches. The sun sets. On Earth, that means a few hours of darkness. Here, the sun won't come back for 14 days. You knew this was coming. You trained for it. But nothing prepares you for how fast the temperature drops. During the day, the ground was 120 degrees Celsius, hot enough to boil water. Now, without sunlight, it falls. Fast. There is no air to hold the heat. No clouds, no blanket of any kind between you and the cold of space. Within hours, the surface drops below -130 degrees Celsius. Near the poles, where your base is, it can reach -250. That is colder than any place on Earth has ever been. Your solar panels are useless. No sunlight means no power. For 14 days, everything depends on one machine, a small nuclear fission reactor. It splits uranium atoms to make heat, and that heat becomes electricity. About 40 kilowatts, enough to power 30 homes on Earth. Here, it keeps you alive. The reactor sits 1 kilometer away from your base. It has to. The radiation it produces is safe at that distance, but you would not want to stand next to it. A long cable runs from the reactor to your shelter. If that cable breaks, you have battery backup. Enough for hours, not days. Outside, there is no glow on the horizon, no city lights, no moonlight, because you are on the moon. The only natural light comes from the stars and from Earth, which hangs in the sky like a bright blue lamp. On the near side, Earth gives you some light. On the far side, there is nothing. You don't go outside during the night. Your suit can handle the cold, but not for long. The seals get stiff. The batteries drain faster. One mistake, one crack, and the cold gets in. At minus 200 degrees, exposed skin freezes in seconds, so you wait, inside a small shelter, powered by a nuclear reactor the size of a car. You count the days until the sun comes back, 14 of them. You survived the night. Now the question changes. It is no longer, can we visit the moon? It is, can we stay? To stay, you need to go underground. The surface of the moon has no magnetic field, no atmosphere, nothing to stop cosmic radiation from hitting you every second of every day. On Earth, you receive about 2.4 millisieverts of radiation per year from natural sources. On the moon's surface, you receive about 380 millisieverts. That is over 150 times more. Stay outside for a year and your risk of cancer goes up significantly. Stay for 5 years and the damage may be permanent. So you don't stay on the surface. You build your base inside a lava tube. Billions of years ago, when the moon was volcanically active, lava flowed under the surface and left behind enormous hollow tunnels. On Earth, lava tubes are usually 10 to 30 meters wide. On the moon, because gravity is 6 times weaker, these tubes can be hundreds of meters wide. Some may reach over a kilometer, big enough to fit an entire small city inside. The rock above you is 40 meters thick or more. That is enough to block almost all cosmic radiation. The temperature inside stays around minus 20 degrees Celsius, cold but stable. No wild swings between 120 degrees and minus 250 like on the surface. Every glass of water you drink was frozen in darkness for longer than anything has been alive. You are building a home inside a dead volcano on a world with no air. And somehow it is working. 6 months in, you feel fine, you feel light. That is the problem. On Earth, gravity pulls on your bones every second. That constant pull tells your body to keep them strong. On the moon, the pull is 6 times weaker. Your body gets a new message. You don't need this much bone, so it starts taking it apart. On the International Space Station, where gravity is nearly zero, astronauts lose about 1 to 1.5% of their hip bone mass per month. On the moon, the loss is slower, but it does not stop. A study on mice in 2024 showed that lunar gravity only partially prevents bone loss compared to full Earth gravity. After 6 months, your bones are weaker. After a year, the damage may take 3 to 4 years to recover if you go back to Earth. Your muscles follow. The ones that fight gravity, your legs, your back, your core, begin to shrink. On the station, astronauts lose up to 20% of muscle mass in a single month without heavy exercise. You exercise 2 hours a day on the moon, every day, using resistance machines. It helps, but it does not fully solve the problem. Then there is your vision. In low gravity, fluid in your body shifts upward toward your head. Pressure builds behind your eyes. The shape of your eyeballs changes. Your vision gets blurry, especially up close. NASA calls this SANS, Spaceflight-Associated Neuro-Ocular Syndrome. About half of astronauts on long missions report changes in their eyesight. Some of these changes last for years after they return. Your heart gets weaker too. It doesn't need to pump as hard. Your blood volume drops. Stand up too fast on a visit back to Earth and you might pass out. The moon is not trying to kill you. It is just slowly forgetting that you are human. The base is no longer a base. It is a town. 300 people live here now. Some are scientists, some are engineers, some run the greenhouses, some fix the machines that keep everyone breathing. Not everyone came from the same country. Not everyone speaks the same language, but everyone breathes the same recycled air. Food grows in pressurized greenhouses, not in lunar soil, not yet. The regolith is fine glass dust with no nitrogen and no organic material. Scientists are working on ways to mix it with fertilizer and use it as a base for growing crops, but at this stage, hydroponics is faster, cleaner, and more reliable. Plants grow with their roots in nutrient-rich water under LED lights. Lettuce, tomatoes, potatoes, soybeans, the same crops NASA has tested on the International Space Station. Enough to supplement your diet, but not enough to replace the supply ships from Earth. Not yet. Oxygen comes from two sources. The fission reactors power machines that split water into hydrogen and oxygen. And the plants help? They take in carbon dioxide and release oxygen, just like on Earth. The colony is a closed loop, or tries to be. Every drop of water is recycled. Every breath is filtered. Communication with Earth works. A radio signal takes 1.3 seconds to reach home. That means every conversation has a 2.6-second gap between what you say and what you hear back. It sounds small. It breaks every conversation. You can't laugh together. You can't interrupt. You can't say, "I love you," and hear it back in real time. After a while, most people stop making video calls. They send messages instead, like letters. But the real weight is not the delay. It is what happens when something goes wrong. On Earth, an ambulance arrives in minutes. A hospital is hours away at most. On the Moon, help from Earth takes at least 72 hours. A rocket must be fueled, a launch window must open, and then someone must fly 380,000 kilometers to reach you. 72 hours is the fastest possible case. In most situations, it is longer. If a pressure seal breaks or a reactor fails or someone's heart stops, you solve it yourself or you don't solve it at all. You look up through the habitat window. Earth is right there, bright blue. You could cover it with your thumb. It has never felt farther away. A child is born on the Moon. No human has ever been born outside of Earth. No one knows exactly what will happen. But the science points in one direction, and it is not good. On Earth, gravity pulls on a growing body every second. It shapes the bones. It strengthens the muscles. It tells the heart how hard to pump. A child who grows up in Earth gravity develops a skeleton strong enough to carry its own weight, about 9.8 meters per second, squared of constant force, pulling down all day, every day, from the first heartbeat to the last. On the Moon, that force is 6 times weaker. A baby born here will grow in 1.6 meters per second squared. Its bones will form under less stress. Its muscles will build for a lighter world. Its heart will learn to pump against less resistance. We know what happens to adult bones in low gravity. They lose mass, they get weaker, and the damage can take years to repair. But adults already have fully formed skeletons. A child does not. A child's bones are still growing, still hardening, still learning what shape to become. In low gravity, they may never reach the strength that Earth demands. We don't know the exact numbers. No child has grown up in 1/6 gravity. No long-term study exists. But the research on fetal development in microgravity, done on mice, on fish, on frogs, shows that gravity plays a role in how bones mineralize, how muscles form, how the inner ear learns balance. Reduce that gravity and development changes. The children born here may be taller, thinner, their bones may be lighter, their muscles shaped for a world where everything weighs 1/6 of what it should. They will run and jump in ways no Earth human can. But the math suggests a terrible cost. They may never go to Earth. Not because it is forbidden, because their bodies cannot handle it. A skeleton built for 1.6 meters per second squared may not survive 9.8. Their bones could fracture under their own weight. Their hearts may not push blood hard enough against full gravity. Their muscles may fail to hold them upright. The first generation born on the moon could be the first generation that belongs to the moon, not by choice, by biology. They will grow up looking at Earth through a window, a blue circle in a black sky. Their parents came from there. Their grandparents came from there. But for them, it is a place they can see and never visit. A planet made of stories. You look up through the dome. Earth hangs in the black sky. Blue, quiet, 380,000 kilometers away. Your grandchildren have never been there. They never will. This is home now.